Morning. Welcome to Krishna's class. Today we develop a theorem for applications, which is known as the partition of complexes. This result is a consequence of the horizontal approach, which we have considered in detail in the last two lectures. So let us briefly recall the contents of horizontal. First, X locally compact. X locally compact. House K compact. B right? Then there exists F belonging to C continuous functions with compact support of X such that F is equal to 71 on K and support of containing. And this is in short notation expressed as okay. Now this is the horizontal. Now we look at one of the applications to derive a very useful tool for our later considerations on connecting positive linear functionals with measures. So let us write down this theorem. Partition. Suppose Pn are open subsets of a locally compact house of space X, comma K a compact subset of X compact and K is containing union of V1 In fact, you know that K being compact, for every open cover, there is a finite subcover. Okay. Therefore, this is something that is coming out of the compactness of it. That is, and we take this V1, V2, Vn such that this is true. Then there exists Hi, Vi, I don't know how to read, for I equal to, this means Hi is CCX, that means Hi belongs to, and support of Hi contained, that's the short form for it. Then there exists Hi belonging to CCX, support of Hi contained in EI for each I running from 1 to n, such that H1x equal to 1 for every x belonging to. It is this part of the statement which says that the unity has been split up in such a way that support of into a sum of n continuous functions with compact support of each Hi is contained in Vi, and such that for every x belonging to K, H1x plus H2x plus etc. Hn x equal to 1, or in other words, we have found a way of splitting up, or there exists a way of splitting up 1 on K subordinate to the existence of sets V1, V2 here. Okay. And such finitely many open sets do exist, because it's not unique, certainly, because every open cover has a finite subcover for K being right. Now we make some remarks. The collection is called a partition of unity. A partition of unity called K. Subordinate to the finite open cover So that's a remark on that. Now we go about proving this theorem. Okay, so what it says is this. Suppose this is K in some X with these are all open VI, which gives a covering. Then what you can do is, I mean, this is K. So you see, so this is your K, and this is your K. Should not be confused. This is your K. I will display it with another. Now what the theorem says is that if this is some VI that you pick, then you see the portion of K, the portion of K in VI is this. Now what we construct is this. On VI, we construct HI belonging to CC VI with compact support inside VI for each I. And such that for X, okay, and such that for X belonging to, you see, that means there is some compact subset of VI which forms the support for your HI, which I lives on that. And then we are having HI subordinate to each VI. So there are some overlaps. There are overlaps of K on VIs. Now you see, these HIs are so constructed that when you sum them up, you will get 1. So that eventually you construct a function h1 plus h2 plus hk whose support lies in where? Lies in V1 union V2 union etc. Vn. And not only that, the sum of HIs on K is equal to 1. We will analyze this in detail. So that is the meaning of the theorem. Later, when it comes to applications, we will see what goes on. Now we will develop that. The first thing that we observe is the following. For every x belonging to K, contained in X, capital X. There exists a neighborhood Wx, that means an open set which contains X such that Wx closure is common. And this follows from the condition that X is locally compact. Okay. Thus, what you have is K is contained in union X belonging to K. Now, since K is compact, implies there exists finitely many points x1, x2, etc., xm, such that K is contained in Wx, Wx1, union Wx2, union etc. Wx. Now that is a consequence of the compactness and the fact that this K is covered by this open sets. Now what we do is for one less than or equal to I less than or equal to n, let Hi be the union of what? Be the union of Vi intersection by union of Wxi which say like Wxj which lie in the closure. And you know that each Wxj closure is compact. So let okay, already defined. So what you can say is that then see some of the Wxj's may not be in Vi. Okay, it's not that all the Wxj closure belongs to Some of them are there. It depends on whether you have excise inside this. Okay. Then because HI is the union of finite union of compact sets. Therefore, it is compact. Okay. Now, each HI containing. So, you have a now new scenario, namely you know that each HI is containing here. So the new scenario that you have is this: HI is a compact subset of EI for each I. So you have got H1, H2, etc. Okay. Yeah. So this is the scenario that we have. So EI and HI is some compact subset. Now what can you say? Now we apply Urison's lemma. Is you know HI and EI. Then by there exists a phi or rather GI CCX such that in fact the support of GI containing and GI is identically equal to 1 on. So this is the first stage of the construction. So you have got now functions, what you call G1, n functions, G1, G2. Now from this we construct these HIs to get the final partition of unity. This itself is not giving a partition. Now we define H1 equal to G. Which I can rewrite, I will do that later. H2 I define as one minus G1 into G. And so on. Hn write as Gn minus 1 times These functions are well defined. Okay. So H1 is essentially defined on P1. I mean, has its support inside. What about H2? Both G1 and G2 are involved. So it is the union of H1 and H2 that comes into the picture and so on. And here the union of H1, H2, etc. Hn that comes into the picture. Right. Now, having constructed these functions, we just rework these functions in such a way that we can use it for our purpose. In that it's a partition T and so on. So let us do that and observe that H1 is equal to one minus G1. We can rewrite this. H2 you can write as, what is H2? H2 is 1 minus G1 into G1. This you can compute and show that this is equal to this you can factor. Sorry. Want to work on this. Now you can show that H1 plus H2 equal to this 1 minus plus what is H2? H2 is 1 minus G1. This you can simplify and show that this is equal to 1 minus G1 into 1 minus G2. Now we apply induction and assume Hk is equal to one minus G1 into etc. 1 minus Gk. Now let us compute then a small computation shows that Hk plus 1 is equal to 1 minus Gk plus 1, and that's very simple computation. So the induction hypothesis is completely valid, and by induction it follows that induction. We have now this is the property that we have worked out on this. So this is the general result that you get on the sum of h1, h2, etc. Now what all things you have? Now you see that this is a see. Now what we want to assert is this. Please. Equal to 1 for every x belonging. This is our important thing. Now you see that it's easily seen that h1, h2, hn are all functions with compact support. Therefore, their sum is also functions with compact support. So that is no problem at all. It directly follows from the definition. Okay. And you see that this the support of these functions is essentially contained in union of v1, v2, etc. Okay, so that is no problem. Now what we get is this. So now we clearly see that. Note that x belonging to k implies x belongs to hi x belongs to k implies x belongs to n, and which implies one of the hi's, and consequently from our definition of GI, it's the consequence is that this at x belong. Why it is so? Because you see, you look at the terms that come. Okay, so you see that h1 plus h2 plus etc. Then at x is 1 minus g1 etc. 1 minus gn. Therefore, gi x is equal to 1 at the point x. So you choose an arbitrary x belonging to k, and you see that at least one of gi's at x is equal to. Okay. Therefore, what do you get? This factor goes. This factor becomes 0. Consequently, h1 plus h2 etc. hn equal to 1 for x belongs. And that's the proof. And clearly, this is a function with compact support. So, now let us see how this actually works. To get a feeling for this, see, you have got h1 and you have got, there may be an overlap. Okay. Now you see that this is going to be, this is going to be inside it. This is inside. This is inside me. Now you see that if you take a point here in h1 but not in v2, okay, x belonging to h1 I am just taking a situation where n is equal to 2. Okay. Then what do you get? At this point, you see that H2 or what you call G2. What is the support of G2? The support of G2 is inside V2. Okay, therefore, at any point on this portion, this is what I am saying, H1 minus V2. So, on V2. Okay. H1 plus H2 is simply equal to, okay. So that is essentially G1. Now on this portion, the same sort of argument, x belonging to H2, but x does not belong to E1. Again H1 plus H2, because one of them is going to 0. The other one takes the value. On this part, okay, on this portion, you can actually see that there is an overlap. So it is likely to have some add-on state. But then here you have this in the definition 1 minus G1 to 1 minus G2 comes into the, and then you just sum them up, finally get this is equal to 1. So you can see that here G1 is equal to 1, equal to 1, and here it is not so, because of course G1 is equal to 1, but G2 is something different. But you see that you have H1 plus H2 takes the form 1 G2 plus which you can also write as G2 plus And from this expression, you can easily see that h1 plus h2 is equal to 1 over here. h1 plus h2 is also equal to 1 over here. h1 plus h2 is equal to 1 over this overlapping space. So you see that eventually our contention that h1x plus h2x plus hn x 1 for all x belonging to K H. Okay. So that is the partition of unity. It's a very useful result. Now you can straight away assume or if the conditions are met, you can immediately assert that there is a partition of unity on subordinate to the open cover that you have, say V1, V2, etc. Very extremely useful. Now you will see the application of this theorem in the proof of the main piece representation. Yeah. Okay, so let me just stop here today because now we are in a position to state the Riesz representation and then go about proving it because it's a longish proof that we have to give. There are various steps to be verified. So it will take 3 lectures or 4 lectures to complete the theorem. So in my next lecture, I will start working on the theorem and its proof. So thank you very much.